Swayam Prabha. Digital India. Educated India.
Welcome back to our lecture series on advanced hydraulics. So, we are still in the module 3, where we are dealing with the varied flows in open channels. So, if you recall the last class, we had discussed on gradually varied profile cases, where a channel of one particular type of bed slope is followed by another channel with a different bed slope. Some of the cases were mild slope followed by another mild slope. In this itself, there were two different cases: milder slope followed by mild slope. Say, I am just giving you a rough idea again. A milder slope followed by a mild slope, that is, this one is having less slope compared to the followed one. Similarly, a mild slope followed by a milder slope. So, mild slope followed by a milder slope, like that. We have discussed the gradually varied flow profiles in these cases. Similarly, another situation is where a mild slope is followed by a steep slope channel. That is, the mild slopes are followed by steep slope channels. Say, you can say a mild slope followed by steep slope, how the profiles looks. Steep slope channels followed by another steep slope channel. So, here also there are two different cases. First, a steeper channel followed by a steep channel, and second one is steep channel followed by the steeper channel. So, today we are now going to discuss on the gradually varied flow profile properties and the concept of transitional depths. So, before starting the computations of gradually varied flow profiles and all, it is better to have some more theoretical background. What are the properties of the slope, water surface profile slope and all. So, for that we will be going in a theoretical way in this particular class. We will start with the concept called control sections. Can any one of you here tell me what is meant by control section, or what is, where the control section is used and what is meant by control section? If you recall the dynamic equation for water surface profile, if you recall the dynamic equation for water surface profile, we had given that as, of course, with various assumptions. We have discarded the correction factors and all. This was the expression for the dynamic equation. This was again represented in terms of section factor and conveyance factors, 1 minus k n by k whole squared by 1 minus z c by z whole square. So, these expressions, what do you understand from this? This is an ordinary differential equation. This is an ordinary differential equation in terms of y. This is a first order ordinary differential equation, and of course, considering the section factors and conveyance factors and all, it is almost true that it is a non-linear. These expressions are non-linear in terms of y. So, this is a non-linear first order ordinary differential equation, and you can solve them using any different solving procedures for the differential equations. As this is a first order this thing, you require one boundary condition to solve this ordinary differential equation. That is the mathematical basis. That is, mathematically you require one boundary condition to solve this particular differential equation. Now, according to the field situation, how will you determine this boundary condition? So, for begin or for solving this differential equation, you can start from the boundary condition in such a way that you know all the type of discharge, means the properties of that particular channel or the section, or you start, that is you start from a particular section the computations in such a way that you know all the properties of that section, that is what is the discharge, what is the various channel properties, all those things, and it is well defined, where properties are well defined. For example, if you have a rectangular weir, the section of the rectangular cross section, it is well defined, and you know if it is a steady discharge coming out from there, you know various properties in that section. So, you can use the rectangular weir as a control section. If you have spillways or if you have sluice gates, those sections are also used as usually used as control section. So, such well defined sections where the properties are known in prior are called control sections. So, usually the control section you start, or you give the boundary condition as any of these control section, and you start the gradually varied flow computations. This is the normal procedure. If you, for example, if I construct a dam and a spillway is there, if this is the normal depth line, critical depth line, then your M1 profile, it will go like this. Okay, this is the way discharge. This is your M1 gradually varied flow profile, and the control section for this gradually varied flow profile. To obtain this gradually varied flow profile, you start from the control section, and the control section is normally given. It is given as, in this particular case, it is given at this location where the discharge and the section details are well defined, okay? And like that you compute. Similarly, if there is a channel intake, for example, channel intake is there, from a reservoir, and if the critical depth line is being shown like this, normal depth line, let us assume that this is having a supercritical flow in the channel intake, and your profile will be something of S1 of this type, sorry S2. So, this is your S2 gradually varied flow profile, and this S2 gradually varied flow profile starts from a control section as shown here. So, this will be your control section now. This will be your control section. So, from there you begin the computations or to determine the gradually varied flow profile in that intake, like that you can determine. This is the flow direction. So, we have to note that usually the subcritical flows have control sections at the downstream of the profile, that is the subcritical flows have control points in the downstream end, as you have seen in the spillway example, say in the previous slide. For the say this the M1 profile, it starts somewhere here and goes like this, but the control section is at the downstream of this profile. Similarly, here this is a supercritical flow, and here the profile is shown like this, and the control section is in the upstream of the beginning of the profile. So, subcritical flows have control sections in the downstream, and supercritical have control sections in the upstream end. This you can just note it down. Now, let us see what are the properties of these gradually varied flow profiles. It is a simple mathematical analysis, or it is not a higher this thing, whatever you have studied in your high school level, and also that will help you in understanding the properties of the gradually varied flow profiles. Again, I am just writing down the dynamic equation S0 1 minus k n by k whole square. Please note that this is k suffix n 1 minus zc by z whole square. In this equation, you can determine the various properties of the slope dy by dx. For that, just recall from the module 1 and module 2. Module 1 was based on the critical flows, module 2 was based on uniform flows. So, in those lectures and all, you have already dealt with section factors and conveyance factor. Section factors and conveyance factors. So, from module 2, or let us go back into the first module. From the module 1, you had studied that at the critical section, the section factor ZC, it can be given as some coefficient C1 into the critical depth raised to m. This was dealt at that time. It was clearly explained to them, where you studied that m is the hydraulic exponent, it is an hydraulic exponent, Zc is the section factor at critical flow, Yc is the critical depth, C1 it is a coefficient. Again, for any section, any flow, if it is not even if it is not a critical flow, forget about it. Still, you can suggest the section factor z square. This is equal to again C1 into y to the power of m. So, this if you have drawn, non-dimensional section factor versus non-dimensional depth. These graphs and all were drawn. You have been taught also how to draw these graphs and all. So, just recall those portions again. Now, we can see that from the two relationship ZC squared by Z squared, this can be given as C1 Yc to the power of m by C1 y to the power of m. This is nothing but Yc by y to the power of m. From module 2, you had been taught about the conveyance factor. which was defined as k squared, that is the for normal flow the kn squared is equal to C2 y n to the power of capital N. C2 is a coefficient and n is another hydraulic exponent. So, this is hydraulic exponent for conveyance factor, hydraulic exponent for conveyance factor. For any flow, even if it is not a normal flow, you can write the conveyance factor as k squared is equal to C2 y to the power of n. So, from these two relationships, you have the following ratio kn by k whole square is nothing but equal to yn by y to the power of n. So, based on these two relationship, that is this one as well as this one, substituting them, you will get in the dynamic equation dy by dx is equal to S0 into one minus yn by y whole to the power of n by 1 minus yc by y whole to the power of m. So, this gives you, means now it is clearly understood by you, means I hope you are able to understand that this equation clearly represents the first order differential equation in y, and the terms of y are non-linear. So, it is a non-linear differential equation, non-linear first order differential equation. So, you can solve to obtain the gradually varied flow profile. So, let us describe the properties of dy by dx. Let me ask you, just recall this equation. From this particular equation, what is what is inferred, or what can you infer from this thing? If the actual depth, of your flow, if it is approximately equal to the normal depth of the flow, then what happens? Dy by dx, or if the actual depth tends to normal depth, then dy by dx tends to 0. That is, the flow water surface profile becomes horizontal there. It becomes parallel to the bed, or it becomes parallel to the bed. What happens now? In the gradually varied flow computations and all, you have to terminate the computations of gradually varied flow. That is, you have to terminate the gradually varied flow computation in such a way that you are achieving either 99% of normal depth if you are starting from a supercritical condition, or 101% of yn when you start from subcritical conditions. So, like this you have to think on that. Why? Because now if the actual depth is tending to normal depth, there dy by dx you cannot, means it is 0, and normal depth phenomenon, it is in the it is only a theoretically possible condition. So, you have to compute, means as we mentioned earlier, dy by dx tends to 0 when y tends to yn. Now, this y tends to yn is possible, or it reaches, or y becomes yn asymptotically. So, you will require a very large length. Say if you are starting, say in this particular case, you have such an obstruction there, critical depth line, normal depth line, and if you want to compute the M1 profile. So, this M1, this gradually varied flow profile reaches the normal depth asymptotically. So, theoretically, according to the mathematical case, it will reach only at an infinite distance. So, that is not feasible for us. We cannot spend that much time, and it is not at all possible. So, we stop the computation whenever you have reached, say in this particular case from the control section, if you have reached 101% of yn, then we stop. We suggest that the depth has reached the normal depth and the gradually varied flow profile is completed, like that. Similarly, in the supercritical flow situations, one can have achieve up to 99% of normal depth and suggest that the normal depth has been achieved, like that you can solve it. Another situation, if your actual depth tends to the critical depth of the given channel, what happens then? This means dy by dx tends to infinity, or dy by dx tends to infinity. What is the physical inference of this particular term? When dy by dx is equal to 0, your water surface is almost horizontal. So, when dy by dx is equal to infinity, your water surface, this becomes almost vertical, and your a vertical state of water surface, it is not at all possible in the nature. So, it is only so whenever it reaches critical state and all, water surface becomes unstable and tries to achieve either the supercritical or subcritical condition as soon as possible. Now, what happens at large depths of y? At large depths of y, that is y tends to infinity, your dy by dx tends to become equal to the bed slope as 0, and also it is almost approximately horizontal. So, at large depths of y, you can note that your dy by dx is almost same as the bed slope. What happens when you reach singular conditions? Anyhow, I am not going to explain in detail various singular conditions, just for you benefit. That is dy by dx is equal to S0 into 1 minus yn by y whole to the power of n by 1 minus yc by y whole to the power of m. In this particular equation, when dy by dx have the form 0 by 0, this is called singular conditions. So, when do you think that it becomes singular? This condition becomes singular if your actual depth y is equal to the critical depth as well as y is equal to your normal depth. So, when this becomes when the flow depth is in this situation, then the singular condition arrives and dy by dx cannot exist in those situations. So, we have to use alternate theories, means, or we have to try to infer subsequent things from this thing. Singular condition occurs when, as mentioned earlier, dy by dx, when it tends to 0 by 0, then the singular condition exists. In that situation, what you have to do is, this situation arises when your actual depth y is equal to your normal depth, and also your actual depth y is equal to your critical depth. When these two conditions satisfy, that means your normal depth is also equal to your critical depth, and this is also equal to your actual depth. If such situation arises, the singular condition then it becomes a singular thing, and it will give rise to various things. So, during the singular conditions, what are the types of depth? How can you compute the gradually varied flow profile and all? You have to understand further phenomenon in that. So, now just forget about the actual depth of water. When for a given channel or when for the given conditions, if the normal depth is equal to critical depth, that is in the channel, both the normal depth line and critical depth line, if they are same, y c and y n, if they are same, then what happens? Due to y c and y n becoming same, it will lead to a means it will lead to transitional depths, a concept called transitional depths. Due to this, that is the normal discharge as well as the critical discharge, if it is same for a particular channel for a given condition, then that will yield transitional depths. So, what are the transitional depths? That is, whenever y n is equal to y c, the corresponding profile will give you the transitional flow profiles. This is for the prismatic channels, your critical depth line as well as the normal depth line, they are straight, right. For the prismatic channels, the normal depth line as well as the critical depth line, they are straight. It is a type of profile. Now, in the transitional flow profiles, there will be a particular, means the singular point will pass through this transitional flow profiles whenever it is required. That is, when the flow gradually varied flow profile, if when you are trying to compute and all, it has to pass through this singular point. Let me make it clear before, that is the transitional, just you right now, just make it that you just note it down that the transitional depths occur when normal depth of flow is equal to critical depth. Okay? The transitional depths occur when normal depth of flow is equal to critical depth. What do you mean by that? From module 1 and module 2, from modules 1 and 2, you just recall that for a given discharge, Q in uniform flow conditions, for given discharge Q in uniform flow conditions, it can be computed using Manning's equation or Chassis equation, whatever be. Let us use the Manning's equation. So, Q is equal to 1 by n a r to the power of 2 by 3 s naught to the power of half. You know what the terminology is in this equation. Like this you can compute the uniform flow. You can easily find, you can easily identify the normal depth yn from this equation. Say if a steady discharge is given to you, some value of q, based on the Manning's equation, you can compute the normal depth yn. So, you can, once you compute the depth yn for the given discharge, what is the critical depth yc, that can also be computed. You can also compute the critical depth, right, yc. Just recall in the rectangular channel what was the critical depth, how the critical depth was measured. Yc is equal to, very easy formula, I am not going to again repeat it here, we will see in another example. For the same discharge q, if you subsequently, now what happens is that, let me state it in the following way. So, this was your normal depth line, this is your critical depth line, or that is, this is your, for the uniform flow, this is the uniform flow with the following normal depth occurring in the channel. If you now increase, that is, and I will change the color and show to you. If you change the bed slope of the channel, what will happen? If you change the bed slope of the channel, you will see that the depth, means the whatever normal depth was there earlier, it slowly starts, means whatever depth or the water depth was there existing, it slowly starts reducing, and it will reach such a state that at a particular situation, say if I raise the bed slope from here to here like this, now the depth of flow will become like this, and whatever depth of flow is there yc, that will be the actual, whatever flow depth is there, that will become a critical depth also, and such a slope is called critical slope, right. This was also explained to you earlier. Your critical slope means when you tilted the bed of the channel in such a way that you tilted it further, means you increase the slope of the bed in such a way that the actual, whatever for the given discharge, whatever discharge is there, that discharge occurs in a critical way. If that happens, then that particular slope is called critical slope. So, I can give the critical slope as S0C. Now, for the given channel, for the given channel, or the whatever possible, means the limit at which you can raise the bed of the thing. If you raise the bed of this thing, bed of the channel beyond this thing, then supercritical flow occurs. If it is lowered further, subcritical flow itself will be prevailing, like that you are aware now. The limit for this particular channel at which the critical slope exists, that is called limit slope. The concept of limit slope is given there, is defined in such a way that smallest possible, it is the smallest possible critical slope for a channel of given shape and roughness. For a given shape and roughness, the smallest possible critical slope of a channel is called the limit slope. We generally give it as SL and all. Let us do one example, and with this example I think it will be more clear for you. Let us do that. I am giving you a problem. A rectangular channel of width B is equal to 3 meters. See, a rectangular channel of width 3 meters. It is carrying a steady discharge. Its Manning's roughness coefficient is 0.05. Determine the limit slope of the channel. So, B is equal to 3.0 meters, Manning's n is equal to 0.015. What could be the critical slope for such a rectangular channel? What could be the limit slope? So, you know that limit slope, it is a critical slope. Critical slope means both the normal discharge as well as the critical discharge are same in such type of conditions. So, what is the minimum possible slope for this particular rectangular channel in which such a condition exists, that you have to determine. First, you have to, the first condition we can suggest is your discharge Q, this is equal to the conveyance factor, and now your slope, it is a critical slope. We have already suggested that the limit slope, it is itself a critical slope. So, the critical slope at which this thing occur, means the minimum possible critical slope is called the limit slope. So, you can measure Q in such a way that this is equal to K S0 C to the power of half, according to the theory that I hope you are well aware of that. Q is equal to 1 by n A r to the power of 2 by 3 S naught to the power of half is the Manning's equation. And now, in this condition S0 is a critical slope. So, that is why I wrote it S0 C. This particular quantity is your K. So, I have written it here. So, I can write Q is equal to 1 by n, and A is B y, A is equal to B y is equal to 3 y, right. So, this is a critical depth as well as normal depth, you can also suggest like that. I am just writing it as C, 3 y c, 3 y c to the power of 2 by 3, 3 plus 2 y c to the power of 2 by 3 S naught c to the power of half. Like this you will get the relationship. Substitute n is equal to 0.015, you will get Q is equal to 1 by 0.015 3 y c into 3 y c by 3 plus 2 y c, the whole quantity raised to 2 by 3 S naught c to the power of half. Substitute the terms, you will get Q is equal to, I have just computed everything, 416.0167 y c to the power of 5 by 3 by 3 plus 2 y c raised to 2 by 3 S naught c to the power of half. So, you do not know the Q and you also do not know the slope S0 c in this equation. So, let me give this as equation number 1. Now, just go to the second condition. The second condition suggests your given discharge is equal to critical discharge. So, from module 1 you just recall them. You had defined section factor ZC. ZC is equal to, for critical conditions, Q by root G. This is same as A into root of D. So, from this relationship you know Q is equal to ZC into root G. This is nothing but A root D into root G. Substitute the quantities. You will see Q is equal to 3 YC into root of YC into root of 9.81. This is equal to 9.3963 YC to the power of 3 by 2. So, I can write Q is equal to 9.3963 YC to the power of 3 by 2. So, this becomes equation 2. So, from equations 1 and 2, that is, you recall equations 1 and 2. This is equation 1 and this is equation 2. So, compare both the equations. From both the equations you can eliminate now the critical depth YC. You can have relationship. You can have expressions between discharge Q and critical slope S0C. Like this, you can have you can eliminate YC from those expressions. So, when I did that, I got the following thing, that is, from equation 2. From equation 2, I got YC to the power of 3 by 2 is equal to Q by 9.3963, or this will give you YC is equal to Q by 9.3963 to the power of 2 by 3. Now, in equation 1, you substitute this YC expression for YC, you will get Q is equal to 416.0167 Q by 9.3963 to the power of 10 by 9 divided by 3 plus 2 y's Q by 9.3963 raised to 2 by 3, this whole quantity raised to 2 by 3, this multiplied by S naught C to the power of half. Like that, like this, you are now getting an implicit expression for Q and S naught C. You will see them, you can just rearrange them. You will see that either you can write Q is equal to, after computing the terms, 34.518 Q to the power of 10 by 9 by 3 plus 0.4492 Q to the power of 2 by 3, the whole quantity raised to 2 by 3 S naught C to the power of half. You can either write like this or just rearrange the terms, means this equation can be rearranged as S naught C is now equal to Q squared into 3 plus 0.4492 Q to the power of 2 by 3 whole to the power of 4 by 3, this entire quantity like that, this divided by 1191.4 49 q to the power of 20 by 9. Like this you are getting the terms. So, you can plot q versus S0c. So, for various values of q, what could be the critical slope? Like that you can slot. I have plotted them and I am just showing it here. So, this is the curve I got this particular in this particular form. So, this is your discharge q in meter cube per second for the given channel conditions for the rectangle. This is your slope, critical slope. So, this is your, this entire curve is your this entire curve is now your critical slope curve. So, why I am showing it here? This curve will be useful for when you do the, when you further try to understand the gradually varied flow profiles. So, I am repeating you in front of you that you just recall, just remember this particular curve, this particular shape of the curve. So, it will be we will be dealing with this particular curve later also. So, this is how you compute the critical slope curve. So, now from this curve it is quite obvious now what is the, say this is this particular portion, whatever is the magnitude, this is giving you the minimum critical slope for the given rectangular channel. So, this is called your limit slope SL. So, the limit slope SL I got from the curve is 0.00408. Okay. So, this is how I got the limit slope. So, now let us come back into the transitional depths. So, when you are at transitional depths, y n is same as your critical depth y c. Therefore, in your dynamic equation dy by dx so, in this equation, when dy by dx tends to S0, what happens? When dy by dx tends to S0, this entire quantity, that is this entire quantity, this has to, this tends to 1. So, when dy by dx tends to 0, this entire quantity now will tends to become 1. That means, your k n by k condition will be equal to z c by z condition. So, that is the slope will be approximately equal to S0 in such situation. This is the condition for transitional depths to exist. That is, transitional depth exists when k n by k is equal to z c by z. So, just note it down again, let me repeat it, k n is now equal to q by root S naught for the normal flow, and also your k is equal to 1 by n a r to the power of 2 by 3. Similarly, the section factor for critical flow is equal to q by root g, refer module 1, and the simple section factor z is equal to a root d. So, this is the section factor for critical flow, this is the section factor for the actual flow, this is the conveyance factor for normal flow, and this is the conveyance factor for the actual flow, actual depth existing. So, the ratio k n by K is equal to ZC by Z can be written as, this can be written as Q by root S naught by 1 by N A r to the power of 2 by 3. This is equal to Q by root G by A root D, where D is your hydraulic depth. I hope you recall what is the term hydraulic depth. So, rearrange the terms here. What will I get? I will get finally a particular relationship n squared G D is equal to S naught r to the power of 4 by 3. Please note this relationship. If this relationship exists, then transitional depths exist. Therefore, in such situation what happens? So, you can compute the transitional depths. Now, what do you infer from this relationship? Only channel geometry and roughness is playing a role for computing the transitional depth for the given slope. Only you can see that only the channel geometry and roughness are coming into picture. So, that is the discharge, whatever discharge is being given to you, that is not coming in, means that is not affecting your transitional depths and all. So, that way one can clearly infer the things. So, we will continue the portions related to this further in the next class. So, as we are not able to complete this entire portion in this thing, there are some few more minutes of transitional depth theories and all left. So, I will continue it in the next class. So, today's quiz. The first question to you is, the control section for a gradually varied flow will be at which location if a dam with regular shaped weir is constructed in a channel having uniform flow. Sketch the location of the control section. I just want to erase this particular portion. This is not ease. If a dam with regular shaped weir is constructed in a channel having uniform, sketch the location of the control section. Your second question for the quiz is, why the water surface tends to become vertical at critical depths? Briefly explain. Why the water surface tends to become vertical at critical depths? Briefly explain. Third question is, what is meant by limit slope of a channel? Briefly explain. So, these three are the questions. So, the solution for today's quiz. For the first question, you are asked the control section for a gradually varied flow if a dam is constructed. If a dam is constructed, and we are, let us assume that the normal depth is greater than the critical depth. In that condition, you will be having an M1 profile like this, and your control section is somewhere here. So, that is just above the top of the spillway, where if you are constructing a weir of a regular shape and all, then that will give you the control section. So, that is your control section. Your second question, why the water surface tends to become vertical at critical depths? Briefly explain. Just recall the dynamic equation, S0 into 1 minus y n by y whole to the power of n by 1 minus y c by y whole to the power of hydraulic exponent m. So, you can write your dynamic equation in the following way also. So, why the water surface tends to become vertical at critical depths? So, at critical depth y is equal to y c. So, this quantity dy by dx then tends to infinity. So, at infinity dy by dx is equal to infinity means it is a vertical line, dy by dx is equal to 0 means it is a horizontal line. Okay. So, that is why it tends to water surface tends to become vertical at critical depths. What is meant by limit slope of a channel? So, what is meant by limit slope of a channel? We had already drawn that. We have suggested that for a given condition, for a given channel section, for a given channel properties and all, the minimum possible critical slope, you can draw the critical slope curve like this. This is the critical slope curve. So, the minimum possible critical slope for that channel, that is called the limit slope SL. I have already explained that in the class. So, this way we are concluding today's lecture. The next lecture will continue some of the portions left in this topic, and then we will go will start the computations of gradually varied flow profiles. Thank you.